Okay, welcome to section 4. Let's jump right in with some sampling distribution is going to be the topic, but we're going to review a little bit and then also kind of lay the foundation with some key understanding. So again, just kind of reviewing the reason we select a sample is to collect data to answer some sort of research question about a population. We use the sample results, whether that's the average or the variance or standard deviation, to estimate the population parameters. Okay. Again, the reason we do that is a lot simpler, um, less time consuming and less expensive for us to do those things. And again, the proper sampling methods and sample results can provide good estimates, and they are just that. They are estimates of the population characteristics. The reason we call these estimates is that there's always going to be sampling error, right? And then the other type of error is that non-sampling error that we talked about, that human error that occurs. So a couple things we want to talk about. One is the sample mean, or X bar. I will refer to it as X bar quite a bit. And here's the formula. Don't get overwhelmed by formulas. We're going to kind of break this down a little bit here. Um, but it's pretty simple, and you're going to see a lot of formulas throughout this whole video and the videos that follow. And so I want you to look at them, but don't be overwhelmed, because we're going to break them down piece by piece. So for example, in this sample mean, finding the X bar, which is simply the average. Everyone knows how to figure out the average, something you learned in middle school and high school. This big E is the symbol for summation. It is the capital E sigma for summation. And this simply says sum up all of the X's. In this case, all the X's are going to be observations for us. And the little I says, how many X's do you have? If you've got 50 of them, don't stop. Go all the way out to the nth X, or nth observation that you have, right? And then you're simply going to divide that by the number of observations that you have. So add them all up. So find all the X's, add them all together, and then divide by n, which is your average, as what most people think of average. I use the word average and mean and X bar to kind of interchangeably. In reality, average describes a set of calculations that help us define what the expected value would be. So average, really, it could be a mean, a median, a mode, an exponential moving average. Average is like a catch-all term, but when I speak about it here, I'm going to be talking about this X bar, the average, as we've come to know it, as most of you know. So in this case, here is our 50 tune-ups again from previous. Each of these are observations. Each of these are x's. So we could easily have a notation back here that says take x1 plus x2 plus x3 plus x4 all the way out. But this little xi allows us to say, hey, take all of the x's that you have, not just having to list them out, because having 50 is actually a small number. Normally, some of our samples are thousands and thousands, taking a sample data of things. Okay. So again, we could assign this x1, x2, x3, x4, and so on. Instead, we simply say xi, and that's an indication to add up all of these observations that we've got here. Okay. The population mean, or the same exact calculation occurs, except for now, instead of a little n, we've got a big N. Big N implies that we have observed the entire population. Little n indicates it's a sample. Big N indicates a population. We also know it's the population because we're looking at mu, and that is a Greek symbol for us. Okay, that is a Greek symbol, so we know it's mu versus the X bar, which is going to be our sample, a Roman letter that we're used to seeing. All right, let's discuss variance. So variance measures how far a set of numbers is spread out. A variance of 0 indicates that all the values are identical. Variance is always a non-negative number. I'm going to show you that in our calculation, but variance is always going to be non-negative. It'll be a positive number. Could be 0, but it'll always be non-negative. A small variance is going to indicate that the data points tend to be very close to the average or the expected value, and hence to each other. So when all the data points are close to the average, they're all really close to each other. A high variance is going to indicate that the data points are very spread around the mean and actually have quite a bit of distance from each other as well. So keep in mind, we're going to see it here in the formula, The value that we get from the variance, the actual number that it spits out after our calculation, is a squared value. So the actual value itself is not as meaningful as the ability to compare the value with other variances because it's a squared number. So let's look at the formula real fast. Here it is for a sample, and here it is for a population. And what this says is we break this down as take xi, or all of the observations, take each individual one, subtract that from the average, the x bar, square it. That's how we get rid of all the negatives, right? We're going to square it and, or in essence, multiply that number by itself. That'll get rid of all of our negatives for us. We'll sum those up, and then we'll take n minus 1, divide that by n minus 1. The reason we divide it by n minus 1 is something to do with degrees of freedom, and we'll discuss that in another video, but just keep that in mind. N minus 1 indicates there's 1 degree of freedom. We do not need to do, when dealing with the population, we do not need to do an n minus 1 because we have the entire population. We have no degrees of freedom that we need to worry about, okay? So again, we square the difference to take care of the negatives. If we just add up all the differences, you'll see this in the video I've created that walks you through the variance of things, but the negatives would simply cancel out the positives and we would end up with 0. All right. So the reason we have to square this is that if we simply added this up here without squaring it, we'd get to 0 every single time. All right. So that's why we need to square it, get rid of those negatives. Standard deviation. Standard deviation is a standard way of kind of what's normal. All right. So it's going to be the square root of the variance. So just here we solve for s squared. In order to get to standard deviation, we're simply going to take the square root of s squared. Okay. Standard deviation is going to tell us how tightly our data is clustered around that average or the mean. And when the data is spread out, we're going to get a flat bell curve. And when it's all clustered around the mean, we're going to get a very high bell curve. And we'll see that here in the next couple of slides. Okay. All right, let's look at the formula. Standard deviation, not that tough, praise the Lord, right? This is simply a S is equal to the square root of s squared. So we're simply taking the square root of the variance. Remember, s squared is our variance. When we find the square root, we get to our sample standard deviation. Same thing here with our sigma. So this is the lowercase sigma. We take the square root of our population and we get to 1 sigma. If you're familiar with the term 6 sigma, this is exactly where it comes from. It comes from the standard deviation. In essence, the 6 sigma process is trying to get 3 standard deviations up from the mean and 3 standard deviations down. Therefore, 6 total standard deviations from the mean, and they want everything to fall within that range. If it's outside of that range, it's a defect. Okay. So for example, if a standard deviation of 3, right down here, we have the average height of men in the United States is 70 inches with a standard deviation of 3. If it is 3, then we know from the empirical rule, and we're going to go through this here in a little bit, 68% of all observations will fall within 1 standard deviation. Okay, so we'd have a height of 3 inches, 67 inches to 73 inches. 68% of all men in the United States will fall within 1 standard deviation of the mean, or they'll be between 67 and 73 inches. Okay, 2 standard deviations. So now I have 3 inches and 3 inches from the mean, so that's 6 inches up, and 3 inches and 3 inches less than the mean, so that's 6 inches down. So it would fall between 64 and 76 inches, and that's going to represent about 95% of all people. And I'm going to show you this here on a chart in just a second. Okay. Let's do a quick review. By the way, this information, if you will go ahead and if you'd like to, you can pause this video and you can watch the variance and standard deviation walkthrough video, but I use these exact numbers. And so what I'd like you to do is I'd like you to come up with a point estimate of the mean cost. This simply means the average. Okay. And then I'd like you to develop a point estimate of the standard deviation. I'd love for you to try it on your own and then watch the video, and it'll step it through how to do that in Excel kind of manually. Obviously, Excel has functions built in, but this is an Excel class, so we're going to focus on some of the math. And you can figure out exactly how to figure out the average as well as the standard deviation. Okay. All right. So if you want to pause the video and do that, that'd be great. And then when you come back, we'll pick up with some of the properties of normal distribution. Okay, normal probability distributions. Some of the characteristics are that it is symmetrical, meaning that it is a mirror image. When I draw a line right down the middle, these two are the exact mirror image of each other. I can fold this in half just like a piece of paper right down the middle, and I'm going to get the exact half up and down from that. Okay. Another characteristic is that the mean, which is our the average, and its standard deviation helps us define the entire distribution, the probability distribution for that. Okay. And then the highest point on the normal curve is the mean, and it's also the median, which is the exact middle of all observations. And the mode is the most frequent observation that we see. Okay. So those all fall right in the middle of our standard deviation. Here's a good example. We have sigma equals 15. Sigma is our standard deviation for a population. When it's 15, this blue line, we see that it is very tight distribution. When our sigma increases to 25, we get a flatter curve with wider tails out here. Okay, and so again, the larger values are going to result in a wider, flatter curve in our distribution. Finally, the probabilities of normal distribution are 50% of the values will fall above the average and 50% will fall below the average. Okay, so the total area under the curve is 1, and we'll have 0.5 or 50% to the left of the average and 50% to the right of the average. If you remember, one of our rules with probabilities is that they all must equal 1. And so all the area under this curve here, all of these data points that fall on this line must be equal to 1 when we add up all their probabilities. All right. This is something that's important, this empirical rule, which for a normal distribution, it gives us, in essence, a way to kind of judge what the probabilities are. So we know, based upon the area, let me go back here, this area under the curve, we know that when I figure out one standard deviation, so when I figure out the average and the standard deviation, let's think about the average height of males in the US. 70 inches is the average, which is right here. And if I know the standard deviation is 3 inches, well, plus or minus one standard deviation, so plus or minus 3 inches, I know that 68.26% of all all observations will fall within that one standard deviation. 95.44% will fall within 2 standard deviations, and 99.972% of all observations will fall within 3 standard deviations. Okay. Again, this is where our 6 sigma comes in because it's plus or minus 3 standard deviations to get to our 6 sigma. Okay. Visually, this is how it looks. So here's our average at 70 inches. 1 standard deviation from the mean down, 1 standard deviation from the mean up, 3 inches in our case, 3 inches, 70 inches, we get to 67, 73. 2 standard deviations. So if the standard deviation is 3 inches, we get to 2 by saying, okay, 3 here, 3 there. That's 6 inches total. So if this were 70 inches, this would be 64. And if this were 70 inches, we get 3, and 3 is 6. 70 plus those 3 is 76. We get to 2 standard deviations, and we would have 95% of all likely outcomes. Again, 95.44%. I'm simply rounding up to 95. Okay? Hopefully that's helpful. All right. The random variable having a normal distribution with a mean of 0 and a standard deviation of 1 is said to have a standard normal probability distribution. And this is where our z-scores will come into place. Okay, the normal random variable is a standard normal distribution is called the standard score or a z-score. So standard score and z-score are the same term here. All right. And in essence, what we're able to do with the z-score concept is we're able to take a unique distribution. So if I was looking at height of people, and I was looking at average tune-ups and what they cost, and I was looking at the cost of a cancer drug, right? They're all on their own distribution. But using a z-score, I can then transfer that to a standard normal distribution. In essence, I can tell people, and it's kind of like this universal code, if you will, in statistics. The standard normal distribution allows me to understand every other unique distribution. So I can easily convert that to um, information so that everyone else can actually understand what's going on. Okay, so the z-score, let's look at this real fast. An observation's z-score, an observation. Remember we had in our tune-up, we had 50 observations. So an observation, each x's z-score is a measure of the relative location of that observation in the data set. So if I were given every observation, every tune-up in our example of 50 is going to have a z-score. Okay, the data value less than the sample. So anytime our tune-up is less than, I think our average was like $79. Anytime our observation, the data value or the x, right, all the same thing, anytime that's less than $79, we're going to get a negative z-score. Anytime it's greater than the sample mean or the sample average of 79, it'll be a positive number. And when we had an observation that exactly equals the average, our z-score will be 0. Our z-score will be 0. So this is what it looks like. If we pulled out from that sample of 50 tune-ups, we pulled out one that had $79. The z-score, boom, is 0. Okay? The z-score is 0. And it allows us to figure out, well, if we had one that was $59, well, 59 is less than the average, so it's going to be down here. It's going to have a z-score of 1 point something or negative 2 point something or negative 1 point something. It will be a negative number because it's less than the average. All right. Here's our formula for z-score, and hopefully this will kind of clarify some things. Z is equal to x, right? Whatever value we pull out from our sample minus the average divided by the standard deviation. All right. So we think of z as a measure of the number of standard deviations x's from the mu. So let's go back here. If I pulled out 59, let's just do that real fast. I'm going to do it on my calculator here. You're not going to see it, but I'm going to take 59 less 79. I forget what the standard deviation was. I'm going to make one up. Divided by, let's say standard deviation was 18. I would get a negative 1.1. So I know that when I pull out a sample of 59, it is negative 1.11 standard deviations from the mean. Okay, so our z-score is a way to figure out the number of standard deviations x is from the average. So I love for you guys to do this. You may not, but I'd love for you to. Let's say this is our entire population here. Let's say that you have the following travel time, and this is all the number of different values in minutes that it takes us to travel. So the mean here, and again, it'd be great if you could work these yourself, add these all up, and make sure you get a mean of 38.8 minutes. And the standard deviation, please walk through that process as well and see if you can't get 11.4 minutes. Well, we can convert each of these observations into a z-score. So to take 26, the first one here, we're going to take exactly what the formula says. The z-score will be x, or 26, minus the average. The average was 38.8, divided by 11.4. Okay, and we get to a z-score of 1.12 negative. This means that this value is 1.12 standard deviations from the mean. Okay. And that's pretty important for us because anytime we can get to a z-score, a standard deviation, we can easily find probabilities. This table, hard to see, I apologize, but nonetheless, it'll give you a feel for these are all the z-scores and the probabilities associated with each of those z-scores. So think about what we've done. We've taken a sample. We found the average, the variance, and standard deviation. From that standard deviation and average, we've been able to figure out a z-score. And then we can figure out the probability based upon normal distribution, what the probability of that number occurring is. Okay, so I'll give you an example. Let's go back to our US males, 70 inches or above. And let's say we were interested in figuring out what the probability of getting somebody who is 95 inches. Let's see, 95 inches is equal to 7 feet 9 inches, right? 7.9 feet. That's a tall person. What is that probability? Well, I could figure that out, right? If I was looking at the average of 70 and I was looking at 95 inches, so 95 divided by 70, I'm sorry, 95 minus 70 is 25. Divide that by 3, I get a standard deviation of a z-score of 8.33. That is a massive z-score. I know that I'm looking somewhere way up here in the tail. The probability is so infinitesimally small, right, that it's not even showing up here. If we look here at negative 3.44, we get to 0.0002 probability. That's a really small chance of that happening. My 8.3 is off the charts, right? It's completely off the charts. And so in this case, we would say that the probability of us getting someone with a 7.9 foot person from a sample would be 0. The probability is so small that it would be 0 based upon the average size. Okay, and that's kind of how that works. So from a hopefully that makes sense as far as just getting to a z-score and everything else. There's a lot of information there, and we can go a lot deeper, and it helps with doing a lot of practice, but for this course we just want to kind of introduce the concept to you. So all right, sampling distributions. The sampling distribution of X. When we look at the population mean that's unknown, what we typically do is we would take a simple random sample of a certain number of elements, a certain number of observations from the population. From that, we'd have sample data, and that would provide an estimate for us, a point estimate of the population. But suppose that we want to draw several samples from the population so that we get a good understanding, a good estimate of what the population is. Well, let's say we had 1,000. Our population size was 1,000, and we decided to pull a sample size, a little n of 10, and we did that 10 times. So we pulled, in essence, a total of 100, but each of these are groups of 10. Each of those groups would have a different X bar. They would have a different sample for us. We would then understand that those are going to have a sampling distribution, right? Some would be a little bit in the middle, some would be up, down. They're all going to be kind of a range of numbers. But from that, we're going to get a distribution, and that's exactly what a sampling distribution does. It gives us kind of a normal distribution. The average of all the samples helps us get a better estimate of the population as a whole, okay? And so what we find is that our expected value of our sampling X, right, our sampling distribution of X, is the probability distribution of all the possible values in the sample. In a sampling distribution, we're taking a bunch of different samples from the population, finding the mean of each sample, and then plotting those means on a histogram. Okay. If our true population actually equals our expected the sample, that's called unbiased. For the most time, we would never expect our sampling distribution of X to be unbiased. It does happen occasionally, but it's only by chance that happens. All right, so our standard deviation of X, again, we'll use the following notation here. Our sigma X bar is the standard deviation of X. The sigma is the standard deviation of the population. The little n is our sample size, and big N is our population size. You'll also hear me say that standard deviation of X is also the standard error of the sample mean. Okay, those two terms are interchangeable. Okay, so the larger the sample size, the more close the sampling distribution will be to the sample mean. Okay, so the actual population mean. And if you think about it, that makes sense. If we take a larger sample size, right? And so if we had a population of 1,000 and our sample size jumped from 10 to 100, right? That is 10% of the population. It's going to be more representative of the population. That's going to make sense to us. If the population is known to be normally distributed, then the sample mean is normally distributed for all values of our sample. If the population is known to be non-normal, then the sample mean will be normal if only a large value. In essence, our sample size is much larger. Okay. All right. So here's the formula. Again, let's not get overwhelmed by these. There are two different phases. We've got a finite population and an infinite population. So let's explain the difference there, and then we'll jump into the formula. A finite population is called finite because it is possible to count its individual members. Okay, it may be called a countable population as well. For example, the number of vehicles crossing a bridge every day, the number of births per year, the number of words in a book. These are all finite populations. The number of units in a finite population are denoted by the big N. All right, thus big N is the size of the population. In an infinite population, usually we're going to have elements that consist of all the outcomes of a process, right? A continuous process that really doesn't have an ending or starting process. So that kind of helps it, keep it in mind for you. The infinite population is what we're probably going to use most of the time. There is a correction factor that happens here. This little square root of n minus little n. This calculation is like super simple, right? And we're just multiplying it by our standard deviation divided by the square root of n, which is just this over here. When we have a finite population, we know we need to use this correction factor, but for the most part, we're going to stick over here, simply taking the standard error of the population and dividing by the square root of n, which is the sample size. Okay, and this will give us our standard deviation. All right, our standard deviation for our sampling error. Okay. All right. The central limit theorem. Central limit theorem is really about sample size and how big the population should be, and can we approximate or use a normal distribution. Here's the big thing that I want you to keep in mind down here. The sampling distribution can be approximated by a normal distribution if the sample size is 30 or more. And if it's known to be highly skewed, we want to go to sample sizes of 50. So I'm going to tell you right now, 50 is the gold standard for sample sizes. Okay, so when you're taking a sample at work, you're doing some outside of the class stuff, 50 is our kind of go-to number that we want to have the minimum. Okay, all right. So a couple of things to keep in mind. If you measure a sample from the wider population, the average or the mean of that sample will be an approximation. We're taking a sample to approximate the mean. Okay. If you measure multiple samples, their means will not all be the same. That'll make sense to us, and will be spread out in a distribution. Due to the central limit theorem, the means will be spread in approximately a bell-shaped distribution. So that's where we can use our normal distribution. The standard error, or the standard error of the mean, of the multiple samples is the standard deviation of the sample means. Right? So when we're taking 10 samples, we get all the averages, we can actually figure out the standard deviation of those sample means, and thus gives a measure of their spread. The standard error is an indication of how likely the accuracy of the sample mean is. So if we get a small standard error, we know that all of those sample means are kind of grouped together, and it's probably more accurate for us than a standard error that's really huge and spread out. Okay, if all of the samples that we've taken and all the means are really, really close to each other, we got a good indication of what the actual population average is. All right. Okay, next concept, binomial distributions. Binomial distributions are exactly as they sound. They have 4 different properties. Binomial means that there are 2 outcomes, success or failure. And again, we're going to define success and we're going to define failure. It's not like, how we normally think of success or failure. Success is you pass the test, failure is not. No, success is, did I get what I wanted? Did I get what I was going for in this experiment? Did we produce a product that didn't have any defects? Okay, that is success or failure. The probability of success is denoted by P and does not change from trial to trial. And then the trials are independent. Again, independent means that one does not affect the other. Okay, does not affect the other. With a binomial distribution, we have charts and we can look things up for a binomial distribution, but we have a way to approximate a binomial distribution. If we have a large enough n, we can actually use our standard deviation, okay? So remember that P is the probability of success on a trial, and it's the same for all trials. So our NP does not change, right? N is the number of trials we have, and then the normal approximation works best when you have a large sample size and the probability of success is close to 50%. Okay. So when we talk about the sampling distribution of a proportion or the population proportion, which is very similar to the concept of a population sample, proportions again are, hey, how many people voted for the president? Well, 52% of the population, that proportion of the population voted. So that's all a proportion is. The sample data provided will be a value for the sample population. And then again, the value of our sample proportion is going to be used to estimate the population. Okay. All right. And so again, our sampling distribution of P is the probability distribution of all possible values. The formula is simply taking your X divided by N. N is the sample size, and X are the number of elements in the sample that possess the characteristics we're interested in. So X would be yes. X would be no, if that's what you're interested in. The proportion is simply the number of successes divided by the total number in the sample. This makes really good sense to us. Again, let's go back to who voted for the president. We sampled 100 people, and 100 people, and 60 of them said, yes, I voted. Well, X is the number of successes, so that is 60 divided by N, which is 100, the total. And here we go, okay? All right. Sampling distribution of P of our proportion is, again, very similar to our sampling distribution of our mean. Very similar concepts with the finite and infinite populations. Those things are the same. So if that's unclear, go back and listen to those sections again. But a lot of times, again, we are going to work towards this infinite population. This is some sort of correction factor that we'll need if we determine that we're in a finite population. But for the most part, we're going to find ourselves in an infinite population. All right. Okay, so binomial probabilities. Here's the simple formulas for them. This simply says that the expected value is n times p. Again, p is the proportion of yeses. P is equal to x divided by n. Okay. The variance is equal to our NP times 1 minus P, and the standard deviation is N, the number in our sample, times proportion, times 1 minus the proportion, and we just take the square root of that. This all seems tough until we actually work some problems in this. It's really not that bad, and again, for this course, you're probably just going to know some definitional things versus, exactly how to work these problems, okay? All right. Again, we can approximate the binomial probabilities with a normal distribution if these situations occur, if a couple of these situations occur. If the probability of x is equal to n, we would use the probability of n minus 0.05. And what it's saying is that a binomial is a discrete deal, right? We're counting these things up. It's a discrete distribution. And the normal distribution is a continuous distribution. Therefore, we got to make these adjustments. This adding 0.5, taking away 0.5 to make those adjustments. And so actually, I've got a sample that we're going to run through here, and I think it's going to make it pretty clear. So let's do that. Suppose a company has a history of making errors in 10% of its invoice. A sample of 100 invoices has been taken, and we want to compute the probability that 10 invoices contain errors. Okay, so in this case, we want to find the binomial probability. Again, we have success and failure. It either has an error or it does not have an error, and that is success or failure. So in order to find the average or our expected, we know that we've got 100 samples, which is our n, 100, and we know the proportion is 10%. So 0.1 times 100 is 10. We would expect to find 10 out of this 100 invoices to have an error. And we want to figure out what the probability is, the proportion of getting 12. okay, of getting those 12. So we can figure out the expected value and the standard deviation by plugging in our numbers. We know that n is 100, p is 0.1, 1 minus 0.1 is 0.9, right? And this is raising it to the half, which is the exact same thing as taking the square root. So we get the expected is 10. Out of this 100 samples, we would expect 10 to have errors with a standard deviation of 3. So plus or minus 1 standard deviation, we would be between 7 and 13. 7 and 13. And we want to figure out what the deal is here with 2. Well, the way that works is that we are going to take our 12 plus or minus 0.5, and we're going to figure out this area under the curve. And we're going to figure out this area under the curve, and we're going to be able to determine the probability. So when we can look these things up in our charts, we need to find the z-score. So we simply take the x minus mu divided by the standard deviation. In this case, we take 12.5 minus 10. Where's the 12.5 coming from again? Oh yeah, we had to add and subtract 0.5 from 12. So we got to 12.5 and 11.5. So we find the z-score of the 12.5 minus 10 divided by 3 gives us 0.83, which corresponds to a probability of 0.7967 on the z-score table. Again, you don't have to do this, but I'm just showing you how we get there. Then we need to find the z-score for 11.5. So if I know that the standard deviation is 3, the average is 10, and 11.5, I can do that math. I can take 11.5 minus 10 divided by 3. I should get 0.6915. Do it for yourself to see, okay? Actually, I'm going to get 0.5, which corresponds to a z-score, 0.5 to a probability of 0.6915. All right. So again, make sure you get a z-score of 0.5 when you do that. And then when I figure out the distance between these two, the difference is 0.1052. So the distance between 12.5 and 11.5 on a normal distribution for this standard deviation and average is equal to 0.1052, which is 10.52%. So the probability of getting 12 errors when we know the average is 10 is about 10%. What's the likelihood that we would get 12 errors out of that 100 sample? It's about 10.25% right here. Okay. All right. Estimating the difference between two populations. We'll cover this real fast. So when we do this, we're simply going to have an estimate of mu1, which is the population for the mean of the population 1, and mu2, which is the mean for population 2. We're going to want to find the difference between those two populations, and then all we're going to do is we're going to take a sample from each of those, and we're going to have those samples represent the population. Okay? And so our formulas, again, not all that important that that you have these formulas down, memorized, but we understand kind of the concept. And the standard deviation or the standard error is simply the difference of our standard deviation from population 1 divided by N1 plus, right, the standard deviation from the population 2 divided by N2, and we take the square root of that. Okay. We don't have to do too many of these calculations, but I do want you to know that you can compare the difference between the populations. Okay. The difference between the populations. We can find the z-score, the probability of getting that difference between those populations. We can determine that information. All right. So sorry for the long video, but hopefully it helps. And then again, please rewatch the parts that you deem necessary. So thanks.